Hello, everyone. We are not having a webinar at our usual time because the speaker today is from Japan, so it's quite late in Japan already. And it's Yuto Sano from Osaka City University. So Yuto, please start.
Okay. Thank you, Jima. Okay. Thank you for giving me such a great opportunity to give a talk here. I also would like to thank the collaborator, Nia, and the supervisor, Makoto, for their great cooperation in my research. Today, I want to talk about the emergent isotropy of a wave-turbulent cascade in the Gross-Pitaevskii model. And this work is motivated by a set of Nia's experiments that study the turbulence of both gases in a cylindrical box trap under anisotropic forcing. Okay. They prepared the ground state of Bose-Einstein condensate in a cylindrical box potential, and they excited the condensate by oscillating force to make turbulence. We numerically calculated these dynamics in the Gross-Pitaevskii model and investigated quantitatively the emergent isotropy in the momentum space. We also found this emergent isotropy is robust for the forcing amplitude, and the dynamics of emergent isotropy does not behave self-similarity with time, unlike the momentum distribution in the inertial range. These are contents of my talk. First, I talk about the background of turbulence and the restoration of symmetry of hydrodynamic turbulence. Next, I would introduce the experiment of the emergence of turbulent cascades in quantum gas, and talk about motivation of our research. Finally, I would explain the detail of our research. I start a general introduction of turbulence. Turbulence is commonly observed in everyday phenomena such as fast-flowing rivers, storm clouds, or smoke, and stuff like that. Also, turbulence is a long-standing problem for fluid dynamics because of the nonlinear properties. And despite the complex fluid motion, we know there are universal statistical laws such as Kolmogorov power law for velocity field of fluid. Here, turbulence has other statistical properties, and that is restoration of symmetry, which is today's main topic. So now I briefly introduce the concept of the restoration of symmetry in the next slide. Okay, let's consider the wake flow for various Reynolds number. The Reynolds number is the ratio of inertial force to viscous forces, and the Reynolds number is often used to predict the flow patterns in the different fluid. In this case, the flow goes from left to right. And for a very small Reynolds number, 0.16, there are symmetric laminar flow for upstream and wake flow. At Reynolds number equals 26, we can see the vortex motion behind the obstacle, and the symmetry of flow is broken. For a more large Reynolds number, 105, the Kalman vortex street emerges. The Kalman vortex street emerges. And then the symmetry of flow is also broken. However, when the Reynolds number is larger than about 1000, a very complex fluid motion emerges in the square area, and the symmetry is statistically restored. In mathematical form, the restoration of symmetry can be found in the deviation of velocity between the 2 point r plus L in the square area. In the in the turbulence, the ensemble average of delta V square is independent of the direction of L. So this means the delta V square has a statistical rotational symmetry. Also, the operation of changing R to R plus R prime doesn't not change this quantity. And this shows the statistical translational symmetry. So thus, at very high Reynolds number or in the turbulence, the sum symmetries are restored. At fully developed isotropic turbulence, the famous Kolmogorov law emerges. In the Kolmogorov theory, the Fourier coefficient of a velocity field is assumed to be isotropic, and the kinetic energy spectrum follows this power of behavior in the inertial range. In the inertial range, we can neglect the effects of energy injection and dissipation. Also, for the three-dimensional case, the energy injected at a large range scale is transferred locally to a small range scale. So this process is called turbulent cascade, and the energy flux is constant. Okay. Next, I introduce the experiment of emergence of turbulent cascade again. In this system, initially, a Bose-Einstein condensate is prepared in a cylindrical box potential. Next, they drop the condensate out of equilibrium by oscillating potential to make turbulence. Here, the oscillating potential was created by magnetic field in the experiment. They observed the momentum spectrum from a time of flight image. Initial TOF image is anisotropic, and this cloud reflects the momentum distribution of a ground state in the cylindrical box trap. The right picture shows the TOF image of a turbulent box gas shaking for seconds. In contrast to initial TOF images, turbulent box gas expand isotropically. And from these TOF images, they calculated the momentum spectrum of turbulence. The vertical axis shows the spectrum, and the horizontal axis shows the wave number. So they observed this power of behavior in this experiment and numerical simulation. This figure shows the simulation result of the time evolution of momentum spectrum of this system. This blue hexagonal dot shows the momentum spectrum at the initial stage. As time goes on, the value at high wave number increases and become a steady state. And the steady state shows the power of behavior. In this system, there are energy injection and dissipation. The injection with oscillating potential is caused at low wave number Kf. So here, L is the height of the cylinder, and And this oscillating potential excites the wave with a wave number 2L. And so in this system, the dissipation is effective in higher wave number than KD. The dissipation wave number KD can be calculated by trap depth UD. And this relation can be understood by the dissipation mechanism of this system. In the initial state, the system is ground state. So the kinetic energy of most particle is lower than the trap depth. Then the particle loss does not occur. However, at the turbulent state, the system is excited by the oscillating potential, and the number of particles with a higher kinetic energy than UD increases. So then the particle can leave the trap, and so the particle loss occurs. This is the dissipation mechanism of this system. They also calculated the angular distribution of TOF images. The angular distribution is defined as this form, and the lower figure shows the angular distribution. So from these figures, we can see equilibrium BC expand anisotropically, but as a turbulent gas expand isotropically. So this means the momentum distribution of both gas changes from anisotropic to isotropic. So this dynamics would be related to the relation of symmetry of turbulence. So we investigate the restoration of symmetry in the wave number space and how this occurs. Okay, I confirm our works. So first, we investigate quantitatively restoration of symmetry by introducing a new measure of anisotropy. The second one is dynamical scaling of evolution of momentum distribution and the relation between the self-similar dynamics and the restoration of symmetry. The final one is the robustness of dynamics with respect to the amplitude of the forcing. So from now, I will explain the detail of our works. First, I introduce our numerical system. We numerically solve this Gross-Pitaevskii equation. The potential term is composed of the box potential and oscillating potential and imaginary potential. So this imaginary potential is introduced to give the dissipation to the system. So this potential works outside of the box and removes particles outside the this blue cylinder. Our numerical system size and number of grid are here. And these are non-dimensionalization parameters. The psi is the coherence length, and this is a characteristic time. Also, in this numerical system, the energy is normalized with a chemical potential mu. And we solved this Gross-Pitaevskii equation by using the pseudo-spectral method with the fourth order longitudinal time evolution. Okay, in this slide, I confirm the dynamics of our system. The left one shows the evolution of oscillating potential. The middle one is the evolution of density distribution. in this region. In this plot, we can see the evolution of the cross section. So the right one is evolution of momentum distribution. Here, the chilled up psi is the Fourier coefficient of macroscopic wave function. So this is dynamics. And the system goes the turbulence, and the system becomes steady. Okay, this is a screenshot of this dynamics. The upper panel shows density distribution. So initial density distribution is uniform, and at later stage, density distribution becomes chaotic and turbulence appears. The middle one is momentum distribution. The initial distribution is anisotropic. However, in the turbulent state, the momentum distribution becomes isotropic. And for reference, I show the projected momentum spectrum. Okay, next, I confirm our particular dynamics. The green line shows the particle loss, and the blue line shows the loss rate. This particle loss dynamics is related to the dynamics in the momentum space. So I show the dynamics in the lower figure. Here, this n bar is the time averaged momentum spectrum over one period of the oscillating potential. Our system is excited at low wave number Kf, and the excitation propagates toward high wave numbers. And when the turbulent cascade reaches Kd at t equal about 90, the particle loss increases linearly, and the loss rate becomes steady after t equal about 200. So, and at the turbulent state, we found this power behavior in the inertial range. Okay, now I move on to the formalization of anisotropy. This formalization is introduced to investigate the k-dependence of anisotropy of the three-dimensional momentum distribution. So we consider this normalized distribution. So if the momentum distribution is isotropic at a fixed k, this normalized distribution becomes unities at the surface. And by using this QKT, we defined the anisotropy of momentum distribution at a fixed k as this form. This AKT shows a distance of QKT to unity, and and the value of anisotropy is normalized to be smaller than unity. So then, if AKT is close to unity, the momentum distribution is anisotropic. On the other hand, when AKT is close to 0, the distribution is isotropic. Okay, let's see QKT in the initial state. The lower figure shows Morwide plot at low wave number k equal 1 and high wave number k equal kd. So in this plot, we plot discretized grid points that perfectly correspond to k equal 1 or k equal kd. And the color shows the absolute value of q minus 1. So the yellow part shows the anisotropic area at a fixed k. From these figures, we can see the anisotropic angular distribution and the value of anisotropy 0.49 and 0.74. I plot the more wide plot at the turbulent steady state. So in the turbulent steady state, QKT becomes almost uniform, and the anisotropy decreases to 0.2 and 0.08. So we can confirm the emergence of isotropic turbulence. In this slide, we show the time evolution of anisotropy and the compensated momentum spectrum. Here, the horizontal axis shows a wave number. And we introduced the coarse-grained anisotropy to reduce the fluctuation on the scale of the discrete momentum grid delta k. At high wave numbers, the momentum distribution increases with a turbulent cascade and becomes more isotropic than the initial values. Then the value of anisotropy also become steady. At low wave numbers, the anisotropic forcing at low wave number kf is dominant. So the momentum spectrum oscillates at low wave number and becomes more anisotropic than initial value. The next, we focus on the dynamics of the momentum distribution for various fixed k in the high wave number region. At k equal k mean, the momentum distribution becomes steady faster than that at high wave number, and its steady value is higher. And for high wave number k equal kd, the value goes steady slowly, and the steady value is low. So from this figure, we thought that we could find an universal curve by rescaling this dynamics with some suitable parameters. The simple candidates of the scaling parameters are the steady value and the saturation time of the dynamics. So this figure shows dynamics at k equal kd. The steady value is, in this case, almost this. In our study, we define the saturation time such as the time when n bar kt over n steady k equals 95%. So at this wave number, the saturation time is roughly here. This figure shows TSK versus K. And the value increases with K, and we can see the parallel behavior in the initial range. Also, we find the power exponent is 1.25. By using the steady value and the saturation time, we rescaled the dynamics of N bar and AKT. Here, the solid line shows the evolution of N bar, and the dotted line shows the evolution of anisotropy. The vertical axis of large figure is rescaled by the steady value, and the black line shows the evolution at high wave number, and evolution at a low wave number, and the green line shows the evolution at high wave numbers. From this figure, we can see the anisotropy goes steady faster than the momentum distribution. So in the inset, the horizontal axis is rescaled by saturation time. So and the dynamics of momentum distribution at different wave number shows almost same curve. So this is a self-similarity of dynamics of the momentum distribution. However, surprisingly or interestingly, we found the dynamics of anisotropy does not show a universal curve. So there are no self-similarity of anisotropy dynamics. The next, we show the power exponent of TSK can be derived by a dynamical scaling. So we start the particle budget equation in the wave number space. This NKT is momentum distribution, and this pi n is particle flux, and F and dkt shows forcing and dissipation respectively. In our case, the particle flux can be written with energy flux and the Bogdanov spectrum. In the inertial range, we can neglect the effect of forcing and dissipation. And then the equation becomes this form. And integrating this equation over a sphere, we can get this equation. At turbulent steady state, equation 1 reads the particle flux is independent of K. Also, at the steady state, the energy flux can be assumed to constant by analogy with Kolmogorov theory. So in this case, so how this relation would behave in the steady state. And so in order to answer the question, we introduce the concept of cascade front. And here is a conceptual figure of the time evolution of the turbulent cascade. In our system, the excitation at low wave number propagate as higher wave numbers and create turbulent steady state from low wave numbers. So when the cascade front reaches this wave number at t equal t1, then in the lower wave number region than KCF, the energy flux and the particle flux is constant. The range where the flux is constant extends to the higher wave number with the cascade. Considering this relation, the value of particle flux is proportional to K cascade front to the -2. So at lower wave number than the cascade front, we can write the particle flux and momentum spectrum in this form. Here, Cp and Cn are constant. From particle budget equation and the relation to, we can derive the time evolution of the cascade front. Here, this equation can be written by the saturation time as this form. Because the time dependence of the cascade front is same as the k dependence of the saturation time. This is more clearly understood by this figure. This figure shows the time evolution of momentum spectrum at k equal kd. If the cascade front reach this kd, the steady state is established then. We can know the arrival time with the saturation time. So we can derive this equation, and the power exponent of Tsk can be derived by the power exponent of momentum spectrum. The fitting result of alpha is 1.25 and gamma is 3.75. So we find these values to be in good agreement. Finally, I introduce the dependence of the dynamics on the forcing amplitude US. The left figure shows Tsk versus K for various amplitude. We can see the dynamics goes steady faster at large amplitude. And also there are polar behavior. The right figure, the right figure shows the steady momentum spectrum for various US. For large US, the steady value becomes large. This means the turbulent cascade for large amplitude transfer a large energy toward high wave numbers. Next, the upper figure shows the value of alpha and gamma for each US. We can see that the value of alpha and gamma are good agreement for each US. And the lower figure shows the anisotropy versus US for each fixed K. This line shows the anisotropy at K equal 1, and this is the anisotropy for K equal K mean, and this is for K equal K max. In each turbulent steady state, the momentum distribution is isotropic. Also, in this range of amplitude, the anisotropy shows almost the same value. But if the amplitude is very low, for example, US 0.01, the steady momentum spectrum would become more anisotropic. And now it is not clear if the system becomes turbulence. So this is related to the problem of turbulent transition of this system. Okay, I summarize this talk. So we studied the development of matter wave turbulence in the ultracold bosonic gas in the cylindrical box potential by numerically solving the GP equation. Introducing a new measure to quantify the anisotropy of the momentum distribution, we uncover that the distribution becomes isotropic from low wave number with turbulent cascade, in spite of anisotropic energy injection. We also find the dynamics of the momentum distribution shows a self-similarity in our case, but the dynamics of anisotropy proceed the dynamics of the momentum distribution and does not show self-similarity. And the scaling hypothesis and the anisotropy of momentum distribution is robust for the forcing amplitude from 0.2 mu to 2.2 mu. Here, mu is a chemical potential. And for future work, we would like to try to consider a theoretical approach of restoration of symmetry in the development of turbulence. Also from this animation, we can see the motion like dark soliton in the initial stage. Yes, this is. And this wave motion nucleate context vortex in this system. So we would investigate the relation between vortex nucleation and wave motion like dark soliton in the initial stage in detail. Okay, that's all. Thank you for your attention.
Yeah, thanks a lot, Yuto. So we're open for questions. Does anyone have any questions? Either raise a hand or just unmute yourself. So I'll ask a question then. So I didn't quite understand. So in the initial distribution, which was anisotropic, so K, Z had quite large values. Why is that?
Okay. You mean this?
Yeah.
Okay. So this initial momentum distribution can be derived by using the Fourier transform. So this result is this distribution is the result of the Fourier transformation of macroscopic wave function. So we solved the analytical solution of this momentum distribution, and then this concentration around the KZ axis is consistent with the analytical solution of Fourier transform.
So essentially, this is a property of the magnetic trap used in the experiment. Is that right?
Sorry, could you say that?
So well, this is just reflects the experimental constraints that the shape of the magnetic trap.
Yes.
Essentially.
Yes, exactly. Yes. So this momentum distribution, yes, I reflect the shape of cylinder.
Okay. Yeah, I see. Any other questions? Yeah. Hi there.
Hello, can you hear me?
Yes.
Yes.
Yeah, so I wanted to ask a question about, I mean, I probably didn't quite follow the argument, but you were talking about you use this equation for the sort of the evolution of the momentum flux, I think, and you express the flux, the energy flux, in terms of the Bogoliubov dispersion relation. Is that right?
Yes, yes, yes.
Yeah, just around here. So I was trying to understand. So the predictions that you get for alpha, I mean, is that so? I guess I'm trying just to understand what you would get if you just had a free particle spectrum versus the phonon sort of branch. I mean, so does it lie kind of in between these two, or is are you dominated by one particular part of the spectrum?
Oh, okay. So initially, the Bogoliubov spectrum is so it's varied. So because initial distribution is uniform, and this Bose-Einstein condensed is dilute.
Mm-hmm.
And so we thought this Bogoliubov spectrum is varied in our system, and so in this case, we assumed the omega k is proportional to k square. So because in the higher wave number region, the Bogoliubov spectrum can be assumed to be proportional to k square.
I see. Okay. So basically, you've really assumed the free particle spectrum to get those comparisons.
Yes. Yes.
Okay. Right. Thank you.
Any other questions? So, well, I have a question about the experiment. Maybe you know the answer. Okay. So, in the experiment, they don't show KZ, so they cannot probably measure it.
Oh, sorry.
So in the experiment, can they measure the KZ? So usually, it's a two-dimensional picture.
In the experiment?
Yeah. Yeah, so usually it's a two-dimensional picture. It's there is no third coordinate.
This is?
Yeah.
Yes. So this is a two-dimensional pictures. So in the experiment, so they calculate the momentum spectrum from these two-dimensional figures. Sorry, your answer is the why.
Yeah, so I was just wondering why. Yeah, is it possible to measure in the third dimension as well? Or it's probably, well, in this symmetric case, it's probably not important. Yeah.
Okay, so from this figure, we can arrive the wave number of particles at this point. Can be estimated approximately as this form.
Yeah, I can see that, but
Yes.
yeah, that's only in 2 dimensions, so it's not, so you kind of assume that it's symmetric about the axis. Or probably.
Yes. So, sorry, I'm sorry. I perfectly I don't understand your question.
Oh, yeah. So yeah, it probably doesn't matter why you cannot measure the 3-dimensional distribution.
Oh, okay. This is a 3-dimensional spectrum.
Mhm.
You say that. Okay. So in this paper, as in fact, when they calculate the 3-dimensional momentum spectrum from this 2-dimensional figure, they calculate the exponent n tilde kr. Kr is the root of the square root of ky square plus kz square. They calculate n tilde kr times k. And so this is a 3-dimensional spectrum.
Yeah.
Yes.
Yeah. Okay. Yeah. So yeah, I get it. Thanks. So any more questions? Well, if not, then well, let's thank Yuto again for giving a talk. So it's quite late time in Japan, and yeah, this was the last webinar this year. So we're taking a break, and I'm hoping you'll have a nice festive season, and yeah, we'll come back to our new webinars. So again, if you've missed any of the previous webinars, they are available on the YouTube channel. So it's getting quite popular. We've had 10,000 views already, which is quite incredible. And there are 35 videos as of now. Okay, so yeah, have a nice break, and we're going to see you next year. Bye.